Hi, everyone. Welcome to the Artificial Intelligence 101, a joint webinar from the Genomic Technologies and Health IT SIGs. Our special speaker today is Dr. Mark Kiel, the founder and CSO of Genomenon. I am your moderator, Daria Ma, cardiovascular genetic counselor from Cedars-Sinai Medical Center in Los Angeles, California, and co-chair of AI/ML subcommittee. A few announcements before we start the webinar. A friendly reminder to the members of the GT-SIG. For those of you who have attended at least one GC-SIG webinar this year and are interested in earning CEU credit for participation, you can be one of 30 members to receive a complimentary CEU application fee. To participate, click on the link from the email Jillian Solito posted on GT-SIG community page from a week ago. In addition, the position of co-chair for GT-SIG is now open. If you're interested in applying or would like to nominate someone, please contact Jillian Solito at jillian.solito@thermofisher.com or refer to the same email she posted on the GT-SIG page from a week ago. During this webinar, please enter your questions in the chat box, and Dr. Kiel will answer them at the end of the talk. Now, it is my pleasure to introduce Dr. Mark Kiel. Dr. Mark Kiel is the co-founder and chief science officer at Genomenon, where he oversees the company's scientific direction and product development. After spending 15 years preparing for a life in academic research, Mark became convinced that a revolutionary change in genomics was more likely to emerge out of industry. In 2014, he founded Genomenon, a life science company addressing the challenge of connecting doctors with evidence in the literature to help diagnose patients with genetic diseases and cancer. Please help me welcome Dr. Kiel.
Thank you, Daria, and welcome everyone. I'm Mark, and I was asked to deliver a non-technical introduction to the basics of artificial intelligence to the interest group. The talk I'm about to give, I've not given before. In fact, I put the slides together mostly this morning. So bear with me as I go through the content with you. But for your benefit, it presumes no prior knowledge of AI or any of its related techniques, and so it remains pretty high level. And the goal of my talk is to simply provide a framework for your understanding, as well as provide a summary description of some concepts and techniques that you've undoubtedly heard about, but may not know in any sufficient working detail how they apply to your everyday life, or even the new products or techniques that you're seeing in the lay press. The ultimate goal, however, is to continue your stimulated interest in learning more about specific aspects of artificial intelligence. As Daria said, I'm the founder of Genomenon, and at Genomenon, I have a very specialized area of focus within computational intelligence known as natural language processing, and within NLP, a very specialized focus at that, which is to say, named entity recognition as it pertains to genetics and genomics. For all these other aspects that I'm going to talk about, I'm an enthusiast just as you are, but also an avid YouTube lecture watcher. And what I wanted to begin by saying is, here are some recommended resources I would commend you to that I found to be particularly valuable as I'm learning about the latest in artificial intelligence. The first is referred to as 2-minute papers by Karoli Sonlai Feher. It is cutting-edge, state-of-the-art descriptions of the latest publications in AI techniques, where there's a focus on image processing, but also some language components. And he's a great mentor to have guide you through the latest research. because of his enthusiasm and his knowledge. So I would highly recommend that you refer to 2-minute papers. They're obviously very short sections that describe the cutting edge research in very succinct clips. The second resource is 3 Blue, 1 Brown, which is run by Grant Sanderson. And he produces very beautiful and clear videographic depictions of mathematical concepts. And his series on machine learning and AI components is particularly relevant to this interest group here. The third is the Lex Friedman podcast, which is formerly the Artificial Intelligence podcast. Lex is a professor at MIT, and he invites a broad array of guests from physicists to philosophers onto his podcast, and they always have very thoughtful conversations. So I highly recommend these 3 resources if you'd just like to learn more about some of these specific concepts that I'm talking about. With respect to natural language processing, there's also the resource of Stanford Online, which particularly for Stanford NLP, films and releases to the public full course lectures from intro coursework all the way to very advanced techniques. And so you can, just as I said before, you can dip in and out of those resources to learn more about some of these concepts that I'm going to share with you. So again, my goal is to provide a bird's eye view of artificial intelligence and to allow you to figure into this framework anything that you had previously encountered but didn't know how it fit into AI generally, as well as anything that you might hear about subsequent to this lecture, so that you'll have a better understanding of the relative importance of and its figuration into AI of what you just learned about. So I'll begin by talking about what artificial intelligence is, characterizing the difference between narrow and general artificial intelligence, talk to the common narrow AI applications, and then describe what is undoubtedly most familiar to you is expert systems, which fall under the narrow AI category. Then next, I'm going to spend some time talking about key concepts in machine learning. The first among them is gradient descent and how it interplays in neural networks. I'm going to briefly describe some of the types of neural networks that you have undoubtedly heard of before, and then describe some of their applications in machine learning by describing those different types of machine learning that leverage neural networks. And then finally, I'll spend the last part of the talk talking about some key concepts in natural language processing. Let's begin by talking about what artificial intelligence is. I'll start with the hype. There's real benefit to artificial intelligence, a great deal of promise and a great deal of productivity already, but there's also a great deal of hype. This is from the CEO of Alphabet, a quote that says, "Artificial intelligence is more profound than electricity or fire." And I've heard it said by others that artificial intelligence will do more for medicine than any of the primary sciences combined. So those are fairly hyperbolic statements, but there is great potential to artificial intelligence, and it comes from the confluence of 3 trends. One is improvements in AI techniques over the preceding decades. Another is the dramatically exponentiated increase in computational capacity and the ease with which practitioners can access that computation on the cloud. And then the third component is seemingly endless amounts of data. And as I'll showcase in some of the slides subsequent, machine learning techniques and AI techniques thrive on this data. And so those 3 trends together are what is fueling this hype cycle for AI. In concert with the enthusiasm is some fear. This is from Stephen Hawking, who exemplifies some of those folks on this side of AI who are worried about its potential applications for harm. Stephen Hawking says here, "The development of full AI could spell the end of the human race." Somewhere in between the hype and the fear is the reality. And many of us on the call are undoubtedly familiar with IBM Watson's foray into genetics and genomics. This is from Roger Schenck, a quote about IBM, which complains from his position as an AI practitioner that they're not doing cognitive computing no matter how many times they say they are. And in fact, this was actually the response from the genetics and genomics community as well, who was unimpressed with the output of IBM Watson's algorithms, which didn't lead to any breakthroughs and didn't facilitate diagnosis in the way that was foretold, and required a great deal of laborious manual training to feed those algorithms to have them have any kind of sensical output. So we're swinging from the hype to the fear and landing somewhere in the reality. This is, as I said, one of the sort of negative consequences of AI in practice, but there are real benefits to AI. And as they apply to genetics and genomics particularly, the challenge that they can rise to is in overcoming what we've referred to as the $1 million interpretation, where the $1,000 genome is producing a great deal of this data and creating a great deal of potential for applications of AI in genetics and genomics. The challenge of understanding and interpreting the data is one that's fairly well suited for AI techniques to surmount this challenge and make genetics and genomics in clinical practice much more widespread and more widely adopted across multiple patient groups. Let's talk about the different types of artificial intelligence that you've likely heard about. So I'll start at the bottom and describe what artificial narrow intelligence is. And that is to say that we use machine or computational techniques to perform a specific task at a level that's equal to or better than human. So that's the whole goal of artificial intelligence, is to use the computation to perform tasks at human level. And when those tasks are narrowly defined, we define that as artificial narrow intelligence. And examples that you'd undoubtedly used or heard of include Siri and Alexa. I just mentioned IBM Watson, as well as Deep Blue, which was recently acquired by Google. At the top level, or sorry, at the middle level there, above artificial narrow intelligence, is artificial general intelligence, which is when computational techniques will be equal to every task as humans. And examples from fiction that rise to this level include C-3PO from Star Wars, and for those of you who've seen these films, Samantha from Her or Ava from Ex Machina. This includes computational consciousness or self-awareness, and demands that there be a theory of mind, which is something that's lacking in artificial narrow intelligence. And then above that, we have a collaborative consciousness or artificial superintelligence, which is to say that AI can work across multiple networks and be better at every human task than humans. And this is exemplified in the form of HAL 9000 from A Space Odyssey. Within the framework of artificial narrow intelligence, we have a number of different aspects and techniques to speak of, three of which in the middle there that I'll focus on, but I wanted to lay out the landscape so that you can frame your thinking and the new things that you encounter under the rubric of artificial intelligence. I'll begin on the left and speak to speech recognition, which includes both speech to text and text to speech. Then in the second from the left is expert systems, which you'd likely have encountered before from Fabric, VAST, and Fever algorithms that are put to use in genetics and genomics to help predict which variants or genes from a patient's sequencing sample may be causative. Similarly, under expert systems are Sophia's DDM system and Diploid's Moon system, which do similar things to VAST and Fever. Moving again to the right is natural language processing, which you've likely used in the past in the form of Google Translate, but also an emerging technique called GPT-3, which can actually generate de novo language from a small input seed and can produce entire paragraphs of human understandable and readable text. Moving further is machine learning, which you may have seen applications in image generation and also in producing deep fakes, which is to say, replacing components of video images with other components, most notably swapping out the faces of one actor with another, which has obvious ramifications for ethical, legal, and social implications. Then finally, and what I won't spend much time on at all, is computer vision and robotics. And the way that you may have seen those is in the form of facial recognition technology, as well as if you've seen any videos from Boston Dynamics Group, where they showcase some of the feats of their intelligent robots. Toward the bottom there, I'm just highlighting that many of these products or capabilities that you've seen span a couple of these parameters. And so these are not neatly defined and exclusive, but there's a lot of fluidity between these different components. And I'm just providing examples there in the form of chatbots or knowledge systems like Siri. I'll start by describing what an expert system is. And again, I'm trying to stay high level. So you have an input or a series of inputs on the left. You pass that input information through a rule-based or inference engine that draws upon a pre-existing knowledge base and passes the processed information through a user interface to the output to answer a specific question that was guided by the user's input. So I'm not going to spend any more time talking about expert systems because I think those are fairly straightforward. And where I want to end my discussion of expert systems is to say that the input and output is fairly stereotyped. The input has to conform to a certain preordained structure, and the output that emerges from the processes in the rule-based engine is stereotyped and predictable. So there's not a lot that's left to chance in an expert system. And that is one of the reasons that it makes an expert system ideal for clinical medicine, is its predictability and reliability. So where I'm going to spend the majority of the rest of the time talking is in the realm of machine learning, which is what most commercial companies refer to or intend to mean when they talk about artificial intelligence, is their use of an application of machine learning techniques to solve specific problems within in their space. And I'm going to, as I mentioned, start talking about gradient descent and how it applies to neural networks, and then characterize those different types of neural networks and different types of machine learning applications. So what is machine learning? And then further, what is deep learning, which is undoubtedly a term that you've heard of before too. Machine learning is the application of statistical techniques to progressively improve computer performance at a specific task without being explicitly programmed to perform that task. And an example of such a task that I'll go through in the subsequent slides here would be image classification, where the input is this a series of pixels in the form of an image that the computer sees in mathematical form, where the machine learning technique would ultimately be able to label that image based on what the image comprises, whether it's a cat or a dog or etc. Deep learning is a statistical method where computers learn to classify patterns in that mathematicalized data, as I said, an image that is rendered as to the computer as pixels using neural networks. So in deep learning, there are networks of nodes with inputs and outputs, very similar to the neurons in a human brain. And in deep learning, those networks are said to be deep when there's at least 3 or 4 of those hidden layers that receive a multitude of interconnections that begin at the input and then emerge on the other side as a succinct output. This is probably the most technical slide I'm going to showcase, but I want to stay high level and keep this abstract. And so this is the concept of gradient descent, and it's a critical component of most of these machine learning algorithms that I'll be walking through in subsequent slides. So on this image, I'm depicting on the axes some output against input on the Y and X axis with a given hypothetical function depicted as the blue line. And by convention, the lowest value of this function is an ideal or optimal output or a solution. So most machine learning algorithms start with some random seed input, which I'm illustrating there as a black dot. They measure the output for that input and then iteratively measure changes to the output based on small changes that are made to the input. So this system, the network that I'll characterize, senses the gradient in its microenvironment as these inputs are iterated and the outputs are calculated, and sensing which is closer to the optimal, or in this case, lowest value, will allow the process to evolve iteratively to descend down to the optimal set point. So this again is called gradient descent. It's an optimization algorithm to find the lowest or optimal value in a given defined mathematical function. That seems easy enough. You might say that the black dot should just roll down the slope. Well, effectively, that is what it's doing. And the gradient descent algorithm is how in this case, the input ball knows which direction to roll in. And what I'm characterizing here is that in my simple diagram on the previous slide, you had a one-dimensional input and a single dimension output. But obviously, if you want to have complex behaviors, you need to have much more complexity in your inputs, as well as in the potential for multiple outputs. And so computational complexities like that require sophisticated data processing. And that's where machine learning techniques that I'll illustrate here in the form of neural nets come in. So the way that that complexity is patterned into the system is through a series of interconnected nodes in a network, much like I'm depicting here, where each node integrates data from the input based on weights and summation functions. So each of the arrows that I'm depicting here has some predefined weight that can be modified as you move through iterations of the system. And each of those nodes performs some function, usually a summation function, on the weights that are defined by those input arrows. The initial input, which, as I suggested, could be a pixelated image of an animal that needs to be classified, passes through the first input layer. The nodes in that input layer then integrate the values and pass those values through the weighted arrows into the hidden layer that is the second layer there in the middle. That hidden layer doesn't directly touch the first layer, nor does it touch the inputs, but rather it remains hidden and becomes an abstraction of some objective parameters that were otherwise seen in the input layer. So you're starting to get more meta understanding of what the input comprises. And the more and more of those iterations through the hidden layers you get, the more and more meta analyses and meta features you can extract from those inputs. And where that information then culminates is into an output layer, which is the summation of all of those iterated, weighted inputs and integrations that will render an output, usually in the form of a statistical certainty, which, as I'll showcase later, can be as simple as, is this a cat in the top node? And in the bottom node, is it a dog? And when you pass the pixelated image through the inputs, as it iterates through those hidden layers, you would get some statistical measure of the likelihood that the input image was a cat or a dog in this case. These networks can get exceptionally complex. This is still a very simplified version of this network, but the complexity will then allow for better and better optimizations and more complex behaviors. And in the case of the image classification with a cat and a dog, better and better, more and more nuanced discrimination of what the input image actually looks like when it's generated as an output. As I mentioned before, if there are 3 or more such hidden layers, the network is said to be a deep neural net. Convolutional neural networks are typically fully interconnected, as is this one, where the weights can be iterated and can span a range of values to give, as I said, more and more optimal output activity. If there's recursion and feedback between these different layers, then that network is said to be a recurrent neural network, or an RNN, which is undoubtedly a term that you've heard used before. So let's go back to the original example that I described, now that you have some sense of how these algorithms are working, at least in the abstract. This is what you see on the left is a cat, though what a computer sees is actually an abstract mathematical representation of pixel values, in this case just black and white, so it's just from 0 to 1, say, would be a way to matricize this input. And they see that data in an XY coordinate. So the value of the pixel density in XY coordinates is actually what the computer sees. So the goal of using neural networks and machine learning for image classification of this image of a cat would be to take that mathematical representation, to train the network in those iterations and modifications of weights and sum functions to get better and better at predicting which of the images that have been supplied by the trainer actually represent a cat. This is a very useful way to represent what that process actually looks like. So on the top, I'm depicting what actually you would be able to recognize if you looked very closely at the pixelated data. And those pixels and the detected edges, which comprise the pixels, and then the fragments, which are a constellation of those edges all put together in two-dimensional space, then eventually culminate into objects, in this case at the top, which are human faces, that can then be recognized based on their statistical likelihood that they do reflect a true human face. And the reason that those different meta layers or meta features are depicted at the top is because that's actually what the information is that corresponds to those different hidden layers in a deep neural net. So again, beginning with the input pixelated layer, the input layer will simply detect the weights of those pixels and their geographic representation in XY coordinate space. And then as you move to the deeper and deeper hidden layers, you'll begin to see features emerge, features that comprise edges, complete white regions or complete black regions, that then, as I say, can emerge into more and more complicated objects or fragments, ultimately culminating, though, as I said, in single output nodes that have been trained through their various weighting and summation functions throughout the entire neural net to be optimized to fire at a high value when the image actually reflects a cat with large eyes, with whiskers, with pointy triangulated ears, with a stubby nose, versus a dog, which would be looking for a different set of features, objects, fragments, edges, and pixels, as you propagate back through the neural net. Ways to apply these neural networks come in a couple of flavors. Here I'm depicting how supervised machine learning works. That typifies what I had just showed before, where you as the trainer trying to pass the input through the neural network to get it optimized to recognize cat images, you will tell the neural network, these are cat images. You will train the neural net to recognize those as cat images. And then when the new input is displayed to that optimized neural network with all of its attendant weights and sum functions, when you present unlabeled images of cats or dogs or gorillas or cars or what have you, only when a cat image is shown will the cat node at the output be optimally firing and give you a high statistical certainty that in fact your input was depicting a cat, versus in this case on the right in the middle, dogs. And this technique of supervised machine learning is obviously useful for classification and for performing regression with your labeled data in the training process, and then with your naive or unlabeled data when you're trying to perform that classification and discrimination. You've likely heard of unsupervised machine learning. It's very similar to what I just described and uses the same neural network techniques, including the core algorithm of gradient descent. The only difference here is you don't begin knowing what your inputs should be labeled as. So what you're asking the neural network to do is actually to perform the discrimination by clustering these different images based on their similarities, based on the neural network's own ability to abstract and recognize those features on its own. Unsupervised learning involves no pre-labeled information and results in a segregation based on those features de novo, without any user prompting. So just as I described supervised learning being useful for categorization, this is useful for clustering, which frequently takes the form of anomaly detection, where you can recognize if some feature in your data, the easiest example to understand is pixelated data, though it could take any one of a number of forms of data, is anomalous and can thereby be flagged for further review or downstream attention to be paid, depending on the nature of the input. Somewhere in between is something called semi-supervised learning. And I'm bringing this up because it's a not uncommon and very powerful new technique of machine learning referred to as generative adversarial networks, or GANs. And the way these work, they have, as you can see, they're depicted, they have their own attendant neural networks, but they have two sets of those neural networks. One is a generator and the other is a discriminator. They're both neural networks. They operate in similar ways to what I described before. The generator, though, in this case, is tasked with taking random noise, passing that random noise in the form of XY pixel values through the neural network to produce faces. And you can imagine how this would benefit from a great deal of iteration. When you begin with random noise, if you pass that random noise through an untrained neural network, if you start to have features of faces emerge, like two eyes or something that looks like a line, you can then provide feedback to the generator to let that neural network know that it has done a better job or a worse job, and have it modify the weights of its own neural network to continually improve and get better and better. So that's fairly straightforward to understand, but the way that you can really energize this GAN system is by having a competition between those auto-generated faces from the generator and what you input on the top there into the discriminator in the form of real faces. So now you've got a competition where the discriminator is charged with determining whether any random input, be it from the real faces that were inserted or the generated faces from the neural network generator, the discriminator will tell if they're real or fake. And in the initial instances of this process, it will be very easy to determine that the generated faces are fake and that the real faces are real. But where it becomes very powerful is when you provide direct feedback from the discriminator to the generator to have that feedback inform how the generator reconfigures its neural network to get better and better at generating real faces. So I don't know how many of you have heard of this, but this is, at least within image processing in machine learning and AI, a very powerful new technique that has, as I say, a lot of LC implications. This is a website to refer to see this in action. It's called This Person Does Not Exist. And so it means what it says here. Each one of these faces is from that website, and it has been created by modifying the GAN to generate plausible human faces from random input data. And so what you're seeing there are photorealistic pictures of people that aren't actual people. So again, if you're interested in learning more about that or actually trying it out, I'd recommend you visit that website. And every time you hit that website, a new face is generated from scratch from that trained face generating generative adversarial network. One other machine learning application that I won't describe in too much detail is referred to as reinforcement learning. And I'll just suffice it to say here that it's unlike supervised learning in that it needn't have labeled data, and it's different than unsupervised learning in that it strikes a balance between the system being more exploratory and trying new things, modifying algorithms, better responding to its environment and its state function, seeking out rewards through better and improved action, and also relying on its previous knowledge to continually get better and better. So reinforcement learning has much more of that feedback cycle where there's better and broader definitions for the punishment and reward system within that network. A couple of the challenges that are widely known and widely cited by practitioners of machine learning are that these algorithms are extremely greedy. So in my simple example about cat images, I illustrated that there were maybe 3 images of cats that needed to train the neural network to discriminate cat images. Well, it's actually many tens of thousands of images. The algorithms are getting more and more refined to require less and less data, but it nevertheless still requires a great deal of data to properly train these algorithms, the most common of which is the first one I mentioned, which is supervised learning. So you can imagine the challenges in machine learning if there's this great need and hunger for all of that labeled data, which typically has to come from manual human labeling. Another challenge here is that these algorithms can often produce inexplicable output. And that was one of the problems with IBM Watson. I refer to that as its opacity, or how opaque the output is. There's recent movements to make the AI algorithms, the machine learning capability, actually describe why they selected the values that they did, or to walk the human user of that network through its process by describing and characterizing which of the hidden layers and which of those meta features were most applicable to generating the final output. Again, that's a work in progress, and it's still a challenge that it's hard for us to as humans to understand what these algorithms are doing behind the scenes. Similarly, these algorithms often are brittle. And whenever you supply them with completely novel inputs, they fall apart, hence the appellation there that they're brittle. As a case in point, there's challenges in self-driving cars, which need to recognize stop signs, where if in some circumstances, if a single pixel in their recognition of a stop sign is out of place, they'll recognize that stop sign not as a stop sign, but as a hippopotamus. And it will have the network, though very thoroughly trained with all of those large data sets, with that one pixel out of place, will inexplicably fail to recognize that what it had seen was actually a stop sign. So obviously there are ways to deal with that in the wild, but it's an illustration of how there's a great challenge with relying on all of these huge data sets to supply the supervised learning that's required to not crumble with novel inputs. And that, as I mentioned, that was a challenge that faced IBM Watson in the genomic space. Similarly, these algorithms are very shallow. And so the way the setup that I described in the naive neural network, as it has to be trained with all of those large data sets for its input, these networks possess no innate knowledge on their own. And you may have heard that there's a challenge with AI in that it lacks common sense. And one of those challenges is in training an AI system, a machine learning application with a specific task, or a series of machine learning applications with multiple specific tasks. the challenge there is to convey to that system as a whole what common sense means. When the ultimate goal of AI is to behave more like a human, common sense is a core component of seeming human, acting human, and that's a challenge facing machine learning, is how to pattern common sense into those systems and algorithms. The last section I want to spend time on here is, again, one of those 6 core components of artificial intelligence, and that's to say natural language processing. So again, this is the area that I have the most experience in within a narrow field of natural language processing, but I'll walk you through some of these concepts that I think you're likely to encounter and benefit from in moving forward. Because I think genetics and genomics most benefits from natural language processing of all of those components of artificial intelligence that I spoke to earlier, I'll characterize what I perceive to be the challenges and opportunities for applications of artificial intelligence in clinical genomic medicine. The first, the upper left, is information overload, which I'm sure we've all experienced here. There's a great deal of information available to us, both from the patient, their clinical case, the sequencing data, or related clinical laboratory values, as well as all of the information that's patterned in empirical studies, related databases, and in your clinical expertise and experience. So there's a great deal of information that needs to be taken into account in order to apply some of these techniques to improve the accuracy of diagnoses or improve the efficiency of reaching diagnoses. Moving over to the upper right there, another challenge is in how unstructured this information is. So I remember when I was going through my medical training, we would take our clinical notes in longhand on a notebook, on a clinical notebook. And only within the past 10 or 15 years has it become mainstream to have an electronic medical record. That's great, but the electronic medical record is still very largely unstructured. Even when you're talking about clinical laboratory values in pathology, where they have they're compelled to fit within certain parameters and conform to specific units, collecting and aggregating and interpreting all of that data still relies on solving this unstructured data challenge. Then at the bottom right there is when we're talking specifically about genetics and genomics, we have the need to have fully integrated pipelines, where otherwise we might have siloed pieces of information, pieces of this puzzle about a given patient and their clinical circumstance, either longitudinally or within that moment in time. The need to have these systems and pipelines be integrated and interconnected and talk to each other in order for us to have the system understand the patient as a whole, that's a challenge and therefore an opportunity for AI to rise to. And then the last on the left and the bottom there is the complexity of the interpretation guidelines for the meaningfulness of these genetic variants. And this is properly a challenge and an opportunity because the guidelines have been codified, and that codification is a great first step in an effort to algorithmatize the interpretation of those variants based on those guidelines, when all of those other components, the great deal of information and data, as well as that information being integrated across multiple pipelines, feeding that information forward into those interpretation guidelines, ACMG and AMP, that's a challenge and therefore an opportunity for applications from AI. So when we're talking about genetic and genomic information, this is how I want to summarize the major problem, which is to say extracting and interpreting genetic information requires a human. And again, that extraction and interpretation can come either directly from the patient case and their circumstance, their clinical laboratory values, including genetic genomic sequencing, as well as information that's been patterned in the empirical evidence in the medical literature. I spoke to those guidelines that you're undoubtedly familiar with, which is to say the ACMG AMP guidelines. Again, a positive movement. They're complicated and there's a lot of subjectivity, but it's a great first step forward to promoting reproducibility and rigor of variant interpretation across multiple labs with disparate data sets and clinical circumstances. The components of this framework that you're undoubtedly familiar with include data that's easy to extract and organize and supply inferences from for a given patient case from relevant databases of population frequency or databases of in silico predictive models of pathogenicity like SIFT and polyphen. So that information is not hard to come by. What is challenging to come by, however, is extracting the information from the empirical literature in the form of those empirical functional studies in vivo or in vitro, as well as understanding the clinical cases or cohort data that precedes your patient case in the medical literature. And then further understanding some of the nuance of the clinical case, such as, is this inherited de novo? What's the allelic data look like, et cetera, et cetera. So all of that requires either literature curation or information digestion from data from within the clinical case. And that's where, as I'm exemplifying here, natural language processing techniques come in. So this is just a smattering of those different techniques, beginning at the bottom with the most straightforward and then moving up layers of complexity and subjectivity. I'll just focus your attention toward the left side here, beginning with tokenization. Tokenization means taking a body of text with human or natural language in it. It may be a PDF of a scientific publication. It may be an electronic medical record describing a patient's circumstance and their treatment history or genetic testing. Tokenization simply involves breaking that text up into its component parts. So basically word identification. Another component of natural language processing that's necessary if you're going to have the machine actually endeavor to understand what this natural language means is part of speech or POS tagging, which is to say, is this a noun? Is this a verb? Is this an adjective? If it's an adjective, to what noun does it apply? Obviously, human language is very complicated and takes many different forms, even when you're trying to describe the same thing. And so part of speech tagging is a critical component to trying to understand what the author's intent was. And again, mathematicalize that information so that that information can then be put into downstream use in these neural networks or other machine learning capabilities. Another facet of natural language processing, and where I specialize, is in named entity recognition. So a named entity is, for instance, recognizing that this word that you've tokenized from the scientific paper actually mentions a gene. And you might say, well, that's easy. That should just come in the form of a lookup table with all of the gene names. Well, it's actually much more challenging than that because some of the gene names do double duty as other English words with non-genetic meaning. My favorite example is there is a gene mice, M-I-C-E. So named entity recognition takes to account character clues, such as the fact that M-I-C-E, if it's uppercased and italicized, is much more likely to be representing a gene than if it's all lowercase and unitalicized. So that's the most straightforward way to do named entity recognition. Another less straightforward way, more subjective, is in taking to account context clues, which comes in the form usually of the surrounding words around that tokenized word that you're trying to name, that you're trying to classify as a gene or a disease or a phenotype or what have you. So tokenization is breaking the text into individual words. Parts of speech tagging is understanding those words in the context of the way that they're used in that sentence. And then named entities starts to get at the import or the meaningfulness of each of those components. and in particular for genetics and genomics, comes in the form of, say, recognizing gene names. And then, as I say, moving up through these layers, machine learning techniques are also applicable to natural language processing, provided that the natural language can be mathematicized. And I won't have time, I'm looking at the clock now, I won't have time to go into detail about how English language can be mathematicized. But for those of you who are curious, I'd invite you to look up the concept of word vectors, word embedding or word vectors, which is simply a way to render the words in some mathematical representation that then allows you to literally perform math on two different words, so that you can say, take the word embedding or word vector for king and the word embedding for queen and add them together and get gender out of that mathematical function of the two word vectors for king and queen. So as I said, for those of you who are interested, there's a great deal of information available in better understanding those word vectors. But then when you understand the meaning of those words through named entity recognition and through some of those word embeddings, then you can start to create a language model, or what these words mean in the context of the whole, the entire paper or an entire body of information from multiple papers. And you can begin to perform something like sentiment analysis. A simple example would be looking at a corpus or a series of chunks of language, like movie reviews, where your challenge in sentiment analysis of movie reviews would be in mathematicizing the language in each of those movie reviews, applying a language model to that input, and then determining whether the movie review was favorable or unfavorable, simply based on that mathematical understanding of the tokenized and tagged information in each of those individual movie reviews. On the genetics or genomics side, you might think of sentiment analysis coming in the form of determining whether a gene, when mutated, has a deleterious effect on the protein or a benign effect in its description of some functional assay that tested the consequences of that variant. And again, each of these parameters, at least in some measure, can be used in the service of doing that kind of sentiment analysis. Critical among them, though, at the onset is getting the named entity recognition correct. And as I mentioned, that's what I specialize in producing the Genomenon, the mastermind database from Genomenon, is in our ability to comb through the medical literature, recognizing genes, recognizing their associated variants, and relating them to the diseases and the phenotypes that they're mentioned in the context of in these various medical reports. So the last thing I'll say here before I turn it over for any questions that the audience might have is the most challenging component of genetics and genomics in the form of natural language processing is getting the named entity recognition of variants correct. So I alluded to the named entity recognition challenge of genes. That's made somewhat easier by the prescribed nature of all the genes and their synonyms and aliases and nicknames in previous versions. So that in at least its initial version involves just looking up that information in a table. It's not so straightforward for variants, as you know, because they can be described in multiple different ways at the cDNA level, at the protein level, at the RSID level, either as a single word or connected string of characters, or otherwise in an English sentence, where you might say the residue at position 1, 2, 3 was mutated from an arginine to a glycine. That is a mention of a variant that would challenge named entity recognition systems that are charged with looking for genetic variants. And as I said, that's what I specialize in at Genomenon and what I've spent the better part of 7 years here perfecting. So I'll conclude where I started by saying that the goal was just to provide a bird's eye view of artificial intelligence to just highlight a little bit the different flavors of AI, the narrow AI, which is for specific tasks, and then the artificial general intelligence, which is to say where machines now are able to learn any one of a number of previously unspecified tasks and perform those tasks at a human level. I'd walked through several narrow AI applications and spent a lot of time talking about expert systems, machine learning, and natural language processing, and provided a little bit of color on specific aspects of machine learning and of natural language processing. So with that, I'll turn it back over to Daria and see if we have any questions in the last minutes of the time we have together.
Thank you, Dr. Kiel, for your insightful and very interesting presentation on the bird's eye view on AI 101. For those who join us later, this webinar is the last of series of webinars from GT-SIG, and you will be receiving instructions to obtain CEU for the series. You may enter your question in the chat box. In the meantime, I have a question. So for some of us who are clinical genetic counselors, or with our doctors, we offer more expanded panel of testings, including even whole genome sequencing. And the labs that interpret the results use AI algorithms from third vendors. So what questions would you recommend us to ask those testing companies to evaluate which algorithm is better than another, if that makes sense?
It's a great question, and I can't give you a specific answer, although I will say that you're right to be skeptical of any outfit in clinical medicine that relies on artificial intelligence techniques. So that's where I spent time talking about expert systems and saying that when the output for a given input is predictable, that is a necessary requisite for clinical medicine. One of the challenges with the application of AI in clinical medicine is the need for it to be reproducible and for you to understand as a clinician the provenance of the final output. So again, that was a challenge with IBM Watson. And what I would say is that it needn't matter as much where the information came from or what the algorithm was that led you to that conclusion, as long as that conclusion is ultimately defensible by data. And obviously the data that is the most valuable is the data in the empirical scientific peer-reviewed body of evidence. That is the best quality data, peer-reviewed, preferably previously reproduced. If you can provide reference citations for any one of those assertions, that is, I think, a necessary component of relying on any AI output for clinical practice. The flip side of that, and a concern where you would want to dig in deeper into the AI algorithm that was used, is the specter of a false negative, right? A true positive, you can see and inspect and verify and know if there's any attendant evidence. With a true negative, that might result from a false deprecation of a gene or a variant because of some error in an AI algorithm. That's where you'd like to dig in deeper into the algorithm. Though, as I said, I can't give you specific information, but getting insight into the rate of false negativity for that algorithm is probably where you'd first like to begin your line of questioning.
Thank you.
Sure.
All right. It seems that we are at the end of our webinar, but I'm sure the conversations will no doubt be ongoing. And thank you, Dr. Kiel, for your presentation, and thank you everyone for attending. Stay healthy and don't forget to vote. Bye.